Hello, welcome back. The title of this lesson is called Solving Radical Equations. This is part one. We're going to have many lessons of increasing complexity of radical equations. Now, what is a radical equation? Basically, it's an equation in algebra where you have a square root or some other root, like a cube root or a fourth root, somewhere in the equation. The left-hand side or the right-hand side, somewhere there's a square root or a cube root or some kind of radical somewhere. And very often, the variable you're trying to solve for is going to be inside or underneath that square root. Right? But not always, but often. And so what we need to do is in all equations, we want to solve it by isolating the variable to one side of the equal sign. Now, in the beginning of this lesson, I want to talk just a little bit because there is a very big gotcha with these kinds of equations. I want to get it out of the way. And then I want to show you very, very quickly and very, I think, powerfully why and how you should watch out for that gotcha. And then we're going to solve several problems to get your practice where it needs to be before moving on into the other lessons where the equations will get even more complex, right? So first of all, you have a radical, which is a square root. Let's talk about square roots for now, but this whole thing applies to cube roots and beyond. So let's talk about square roots. What you want to do is you want to get the square root or whatever radical you have to one side of the equal sign so that you can undo the square root. Now, how do you undo a square root? We've talked about the opposite of a square root is a squaring operation. So if you square a square root, basically they nullify each other and they both poof disappear, and then you have what is underneath that radical kind of off by itself now. So if you're trying to get the variable that's underneath that radical to come out of the radical, you need to square it, and that will then do that for you. So what you're going to end up doing is move everything around to get the radical to one side. You're going to square both sides, and then you're going to solve for the variable. Sounds great. Here's the very big gotcha. When you solve equations that have radicals in them and you square both sides, you need to be very careful to check all of the answers that you get, to take those answers and plug them back into the original equation that you were given and make sure that both of the answers or all of the answers that you have are actually correct solutions. Because what's going to happen is in some cases they'll be all correct. In some cases you're going to find what we call an extraneous solution. We actually mentioned extraneous solutions in several lessons ago, maybe 10 or 15 lessons ago, when we were talking about other types of equations, complex equations, where we were canceling terms on the bottom, and sometimes we can have extraneous solutions. We need to take those solutions, plug them back in, and see if they actually still satisfy the equation. Now, I want to get into a little bit of theory, not too much, but a little bit to explain to you why you have to watch out for this, because I was never taught that when I learned algebra, and I always hate it now that I'm a little older and I understand why these things are the way they are, at least more. And I feel like students should know a little bit about where it's coming from. All right, so you have this thing called an equation in algebra. We've learned about lots of equations, but let's take a very, very simple one. Let's say we have 2x plus 3 is equal to 5. Now you know how to solve this, right? Because you take the 3 and you move it over, then you divide by 2. So the first step is you say, it's going to be 5 minus 3, so you're going to get a 2. And then you divide by 2, so you're going to say 2 over 2 is 1. So the answer is 1. 2 times 1 is 2. 2 plus 3 is 5. So it checks. That's the correct answer. But notice, what we've really said is, addition and subtraction and multiplying and division of both sides of an equation are what we call linear operators. What it means is when you add or subtract to both sides or multiply or divide to both sides, the new equation you get, notice that every step of the way we kind of get a new equation. The new equation you get is going to have the exact same solutions as the parent equation. So when we subtract the 3 here, we get this equation. This equation has the exact same solution as the parent equations. Why? Because adding and subtracting and multiplying and dividing are what we call linear operators. They're very well behaved. You can do the addition and undo it with the subtraction with no problems, and it gets into a lot more theory of math that I don't want to get into now. But that's the basic reason why. It's because addition and subtraction can, when you do them, they can be undone what we say linearly, which means they can be undone without any problems. But here in these equations, what we're going to solve here, we're going to be squaring both sides. Squaring is a different operation than adding and subtracting or multiplying and dividing. Squaring is what we call a nonlinear operator. When we square something, it by definition isn't always able to be undone in the same way as addition and subtraction can be. So because of that, when we square both sides, the new equation we get might have actually more solutions than the original equation. But it's guaranteed to have, it is guaranteed to give you all the solutions of the parent equation, but it also might give you more. That's basically what it boils down to. So when you square both sides of an equation, You are guaranteed to get all of the correct solutions to the parent equation, but the squaring process might actually introduce some other totally incorrect solutions, what we call extraneous solutions, because squaring is not a linear operator like addition and subtraction and multiplication and division. I'm going to show you a little bit more about why that is as we get through it here. So the bottom line is when you square both sides of an equation, you need to take your answers and plug them all back in to see if they're all correct. Some of them might be correct and some of them won't. The ones that aren't are called extraneous solutions or extraneous roots. You just basically mark them off and say they're not correct, but the solution process will always give you the correct solution as well. Those are the ones that you actually circle for the answers, right? So let's crawl before we can walk. I do want to talk about that more because I think it's important that you understand this a little bit better, but let's crawl before we can walk. Let's take a very simple radical equation. Square root of x is equal to 5. Now we have never solved an equation like this before. The variable is underneath the radical, and then over here is a number. So obviously, like in this problem, we did addition and subtraction and so on, but addition and subtraction, multiplication and division are not going to save you in this problem because the x is underneath the square root. So we have to undo the square root with the opposite, which is squaring it. We can do it to both sides. So we're going to take this square root of x and this 5, and we're going to apply what we call the squaring operator. You know, instead of adding and subtracting and multiplying and dividing, we're going to square both sides, but the squaring is not a linear operator. I know that that's a crazy, fancy sounding term, but what it means is it might introduce new solutions that aren't actually valid for the original equation you have, because squaring is just a slightly different animal than straight multiplication or addition. But in any case, the square and the square root we can think of as canceling, so we'll have an x left over, and then 5 times itself is 25. So this is your final answer. You only got one answer, so what we need to do is, before we circle it, we go over here and we check it. So what I write is I check x equals 25. And what I do is I plug it in here. I say, is the square root of 25 equal with a question mark to 5? And I all know that the square root of this is 5, so that it is equal to 5. So yes, it's a valid solution. Now only at this moment can I circle the answer. So what you do is you get your answers. Before you circle it, you check them. If you have 3 answers, you check all 3 of them. And then the ones that pass the test are the ones that you circle. Now it's very important that you take and you plug this in to the original equation, the very one that you started with. Don't plug it into any of these others in the middle part here. You always go back to the beginning. All right, so let's do another really quick and simple one like this, and then I'm going to talk to you a little bit more about the theory behind why you have to be careful. Let's take a look at x minus 1, square root of that is equal to 3. Again, my variable's underneath the radical. I have to get rid of it, so I'm going to do the opposite. So x minus 1 square root. How do I get rid of a radical? A square root specifically, I square it, and that means I have to square both sides. So I can think of the radical canceling with the square, leaving me x minus 1. 3 times 3 is 9. And now, of course, I can move the 1 over by addition to make 10 on the right-hand side. So I think it's correct, but before I actually circle it, I go back and I say, all right, I'm going to check x is equal to 10. I'm going to plug it in here. 10 minus 1, square root, equals question mark 3. 10 minus 1 is 9. Equals question mark 3. And I know you all know that 3 is equal to 3, so this is a correct solution. So this is the correct solution because it satisfies the original equation. Now suffice it to say that sometimes, in fact the last problem we're going to do in this lesson, I very much want you to get to the end of this one so you can see sometimes the solutions won't work. So that's going to be at the end. But before we get there, I want to motivate you just a little bit more as to why this squaring thing, why does the squaring thing behave so differently? I keep calling it like a nonlinear operator. It sounds very confusing or very fancy. But what I'm basically trying to show you is that when you square things, sometimes it changes the equation so much that you get too many answers, that some of which are not even correct solutions to the original problem you have. And in order to illustrate that, I want to do it with a very simple example. Let's take an equation, but a very, very simple equation, a really simple equation. Here's an equation. X is equal to negative 1. This is actually an equation. How do you know that? Well, because it's got an equal sign, it's got some variable in there, and it's got a number. This is just a negative number. But anyway, this is an equation. Now you might say, well, that's a dumb equation. It's already solved. Well, of course, it is the simplest thing I can think of. But it is an equation because I have a variable equals something. It just so happens I don't really have to do anything to subtract or anything to solve for x. I've already done it. So this is an equation. Now, if it is an equation, and I can do what I want, more or less, to both sides of an equation, I should be able to square both sides of this equation. And that's what I'm going to do. Let's just square both sides. Why not? We can do a square to we can do anything we want to both sides, right? So let's square both sides of this. Well, if I square the left-hand side, I'm going to get x squared. If I square the right-hand side, I'll have -1 squared. So really what I'll get is, what's -1 squared? That's -1 times -1, giving you a +1. All right? So I get this as an intermediate equation back. And then let's, I'm sorry, I have x squared here. X squared is equal to 1. And then I get this guy right here. And then I say, okay, so what I did is I squared it and I got this back. But let me go ahead and solve this, because when I'm, what often happens in algebra is you think, well, I can do anything I want to both sides. I'm going to square that equation, and then I'm going to solve it again. I should get the same thing back. So here I squared it. I got a new equation. Now let's solve this guy. How do we solve it? Well, we take the square root of both sides. So I'm going to have this x squared. I'll take the square root of it, and I'll have this 1. I'll take the square root of that. I'm just doing the square root to both sides. So when I take the square root of this, what do I get? I get x, okay? And what do I get on the right-hand side? I have, remember when I apply a square root to both sides, I have to add a plus or minus myself. So I'm going to get plus or minus 1. So what I figured out is that x can be equal to 1, but x can be equal to -1. But look at how crazy that looks. The equation I started with was just a single thing. It said x is equal to -1, period, end of story. But by squaring it, and then getting down to this point and solving this equation by going the opposite way, square rooting it, you see I actually got more solutions than I started with. So this guy is an extraneous, this is an extraneous solution here. It's not even part of the original equation. It doesn't satisfy the original equation because -1 is never equal to +1. This guy, of course, is a solution to the original equation. It is the same exact thing, but this guy is not a solution. So I'm trying to show you by the simplest example possible that squaring both sides of an equation can change the equation in such a way to introduce more solutions. And that's because the squaring operation and the way square roots work and the way the plus minus comes into it, we've already talked about all that a long time ago, can introduce extra solutions. This is the simplest one I can think of. So when you get down to the point where you have to actually square both sides of any equation, check it to make sure that all of the solutions are valid. And in the last problem that we're going to do here, there will be an extraneous root. One more thing I'll say is that when we did these simple problems, we changed the equation to this, and this equation here, we know because adding and subtracting is linear, that the answers to this equation are the same exact answers as this one. But when we square an equation, what we're saying is that we're guaranteed to get all of the correct answers to this equation that exist, but we might also get some extra ones. So when you square it, it's not like it's going to give you garbage. It's going to give you all of the correct solutions. In this case, it's just this one, but it also might include some extra ones that are extraneous, and that's why we need to filter through those. So you don't have to worry about it giving you junk. It's always going to give you the right answer. It also might actually give you extra stuff. Okay? All right, so let's go and crank through now that we have the theory out of the way and do some problems. What if we have 4x minus 3 square root around this equals 5? We have the radical on one side already, so we're going to square both sides. 4x minus 3, here we're going to square it, and this will be 5 squared as well. The square and the square root cancel, so we have 4x minus 3 is equal to 25. We can now add 3 to both sides, so we have 4x is equal to 28 because 25 plus 3 is 28. And then x can be equal to the 28 divided by 4. And then we now know that x is equal to 7. But before we actually circle it, we have to check. So we check x is equal to 7. Whoops, if I can write the number 7 correctly, like this. We got to put 7 in here. 4 times 7 minus 3, square root equal, question mark, 5. So here I have 28 minus 3. 25 is the square root, and that is equal to 5. 5 is equal to 5, and this guy is correct. Whenever you do this thing and you only get one answer, it's always going to be correct. It's just the cases when you get more than one answer you really have to watch out for. But still, it's a good habit to take the single answer that you get and just double check yourself and make sure that you're getting everything correctly correct in your final answer. Slightly more difficult, but not too hard, is 3 times the square root of x minus 5 is positive 13. Now we want to get all the radicals to one side if possible, so we need to get rid of the 5 by adding it. So we have 3 square root of x equals, we'll add the 5. 13 plus 5 is 18. Okay. Now, I could square both sides as it is, but since I know that I can divide by 3 and then 18 divided by 3 is a very nice number, I'll divide both sides by 3. 18 divided by 3, so the square root of x is 6. And now I have this equation, which I can then solve by squaring. I'll square this side, and I'll square this side. This will cancel, giving me x, and then I'll have 30. I'll have x is equal to 36. And so I need to check that. So I'm going to check x is equal to 36 and see. So I'll put 36 in here. 3 times square root 36 minus 5. What does this equal? The square root of 36 is 6. This is 18 minus 5. And 18 minus 5 is 13. That does equal 13 on the right-hand side, so this is the correct answer. Again, when you get down to the point and you only have one answer, it's going to be correct. I always want you to check it in case you have the real weird, crazy equation I can't predict ahead of time, but in all cases I can think of, when you get a single answer by doing this process, if you've done it correctly, it will be correct. But it's the cases when you get more than one answer when you really have to be careful. And an example of that is this very next problem that we're going to do right now. So let's go ahead and tackle that one. What if you have, let's see here, what if we have 2 times x squared minus 7, radical surrounding this, equals 5. How do we solve that? We're going to square both sides because the radical is already on one side by itself. So 2x squared minus 7 square root, I'm going to square the left-hand side, and then I'll have a 5 squared on the right. The square and the square root will cancel, so we have 2x squared minus 7. That's going to drop out on the left, 25 on the right. 25 on the right. All right, so then I'm going to move the 7 over by addition. I'll have 2x squared, and then when I add 25 plus the 7, I'm going to get 32. And then I divide by 2, I'll get x squared is equal to 32. Divide by 2 will give me 16. So how do I solve this? I have an x squared equals 16. We've solved equations like that. We have to take the square root of both sides. So you'll say x is equal to, and then we have to add our plus and minus when we apply our square root, like this. And so we'll have x is equal to 4, and x is equal to negative 4. We have 2 answers to this. We think there's 2 answers to this. But before we circle any of them, we have to check both of them. So we go up here, and we say we're going to check x is equal to 4. We're going to put it in here. So I have 2 times 4 squared minus 7 square root of this. Is this equal to 5? So let's crank through. We have 2 times, this will be 16. 2 times 16 minus 7. 2 times 16 is 32 minus 7. 32 minus 7 is 25, so we'll have square root of 25. And what I'm going to get is 5 is equal to 5, which is equal to the right-hand side. So the answer of 4 is valid and is correct. So then, most of you can see that it's going to work out perfectly fine as well with negative 4, but let's go ahead and put it in there. So we'll have 2 times negative 4 squared minus 7 equals question mark 5. We have a square root around this whole thing. You can see it's going to be the same thing because this negative 4 squared is just going to be 2 times 16 minus 7 again, which is exactly what I got here. So you can see that it's going to end up being the square root of 25, which means 5 is equal to 5. And then the negative 4 in this particular case worked as well. So there's actually 2 answers to this equation, positive 4 and negative 4. So you see sometimes when you get extra answers, more than one answer, they can both be valid. But in this very last problem, which I've reserved for the last board because it's longer, we're going to find out that not all of the answers are valid. And they're extraneous because the squaring process sometimes does that, and I tried to explain why, and that's why you have to be careful for it. Be careful of it. So here's our last problem. What if we have 3 times x minus 5 times the square root of x equals 2? Well, we want to get the radical to one side. So we're going to take the 3x and we're going to move it over here, or we could just take the 2 and move it over and the 5x over here. It's just different ways that you want to do it, but basically I want to get the 5x off by itself. So let's move that over here. We'll say 3x is equal to 2 plus 5 root x. I just take the 5 root x, move it over there. And then I want the radical by itself, so I want to get rid of the 2 by subtraction. So it would be 3x minus 2 on the left, 5 root x on the right. Now you see, what I'm going to end up doing is squaring both sides. Now I told you in a previous problem, let me pull it up. Where is it? Right here. I got to this part here. I went ahead and divided by 3 to get the square root completely by itself, but the reason I did it is because 18 divided by 3 was a nice number. Okay? But here, you see, if I divide by 5, I'm going to have 3x minus 2 divided by 5. Nothing is very pretty over there. It's going to be an ugly fraction. So what you want to do is, if you can get the radical completely by itself, including any coefficients, dividing them away, then do it. But if not, then just leave the coefficients in front. It's still going to be fine. You just want the radical term to be by itself. So on the left-hand side, we're going to square both sides. We have 3x minus 2. We'll square this. And then you have to wrap it in parentheses. 5 times the square root of x will square the right-hand side as well. Now, what does this mean? It means that this is 3x minus 2 times itself, 3x minus 2. And what does this mean? The square applies to the 5 and also to the square root of x, right? Separately. So when the square applies to the 5, 5 squared is 25. And then the square root of x, or the square of x of the square root of x, they cancel, and so you get x. So 5 squared is this, and then this squared just means the x drops away. So you see you have x's everywhere, and you want to collect them. So what you have to do is multiply this whole thing out, and then try to get all the x's together. So 3x times 3x is 9x squared. The inside terms will be negative 6x. The outside terms also will be negative 6x. The last terms, negative 2 times negative 2 is positive 4. And then we still have 25x on the right-hand side. So we have 9x squared minus 6 plus 6 is 12x plus 4 is equal to 25x. Now we want to pull this over. So what is negative 12 minus 25? Or another way you can think of it, what is 12 plus 25? It's 37. So you're going to have 9x squared minus 37x, because we're subtracting it, so it's negative over here, plus 4 equals 0. Now, forget about all this stuff. If I just gave you this equation and said solve it, you know how to do that. Or you know how to at least try to do that. We try to always factor first. So we open up 2 sets of parentheses, set it equal to 0, and we factor it. Now there's unfortunately a lot of different ways you can factor, because 9 can be 3 times 3, but also 1 times 9, and then 4 can be 2 times 2, and also 1 times 4. But what you're going to find out is that the factorization that works is 9x minus 1, and then x minus 4. How do I know this one works? Well, because these guys multiply to give me the 9x squared. These guys, the last terms, multiply to give me 4. These inside terms give me negative x, and these outside terms give me 9 times 4 is 36, so it's negative 36x. When I add them, I get the negative 37x. So that's the correct factorization. So this term can be equal to 0. 9x minus 1 equals 0. Or this one, x minus 4, can be equal to 0. So I can add the 4, making x equal 4 over there. And then this one means 9x equals 1. I can add the 1 over, and then x is 1/9 by subtraction, or by dividing by 9. So I have 2 answers. Notice that in the previous problem, I also got 2 answers, and both of them were correct. I circled both of them because I checked both of them. Here I also have 2 answers, but I have to check them both. So let's take this and go all the way back up at the top, and I'm going to check x is equal to 4. So I'll put 4 in here. 3 times 4 minus 5 square root of 4 equals question mark 2. This is 12 minus 5 times square root of 4 is 2. And then this is 12 minus, what is this? 5 times 2 is 10. 12 minus 10 is 2, which is also equal to 2. So this is correct. And the answer of 4 is one of the solutions. This one right here is 1/9. Let's check 1/9. Let me switch colors, actually. We're going to go over here and check x is 1/9. So we're going to put 1/9 in here. So what we're going to get is 3 times 1/9 minus 5 square root of 1/9 equals question mark 2. So what we're going to get is 3 over 9. 3 over 9, when you do the fraction simplification, you should see that's 1/3. This is multiplied to get 3 over 9, which is 1/3. And then here we're going to have 5 times, what is the square root of 1/9? It's going to be 1/3 because the square root of 1 is 1, and the square root of 9 is 3. So you're going to get 1/3 here. So you're going to have 1/3 minus this 5 over 1 times the 1/3 will be 5/3, right? And then what you're going to get down here, we have a common denominator, so 1 minus 5 is -4/3, but that is not equal to 2. No matter how much you want it to be, it's not equal to 2. You're going to have an inequality here, so that means this is extraneous. I'm sorry, not this one, because I already circled this one. This one's extraneous. And what does extraneous mean? It doesn't mean that you've done anything wrong. It just means that for this particular equation, the act of squaring both sides changed it so that the new equation that we got, this one, or I guess after you square it is this one, the solution to this equation contains all of the solutions of the original equation plus one more. So it always gives you the correct answers, but it also gives you some others, because when you square both sides of an equation, sometimes you change it so much that it has extra solutions which aren't even valid anymore. And that's because squaring is a nonlinear thing. It doesn't behave the same as addition and subtraction to both sides of an equation. So we learned in this lesson a lot. We did a lot of theory of radicals. We said if we have radical equations, we want to get the radical to one side. We want to square both sides. And then we talked about the theory of why we have to worry about it. And I showed this example to give you the most simplest equation I could come up with. This is an equation, even though it looks solved already. When you square it, you get this. You turn around and solve it by the square root. You would think that it's kind of like adding and then subtracting in an equation. Immediately undoing itself should give you the same answers. But with squaring and square roots, you can actually get extra answers that encompass all the original solutions but have extra ones that aren't true. So you have to check every one of them. And we showed an example of that here. So we have 4 more lessons in solving radical equations. We have a lot of ground to cover to give you a lot of practice. So solve all of these, follow me on to the next lesson, and we'll get very, very good by solving lots of problems with solving radical equations.